Yeah, so arguably the most important part of designing something open source is the actual design of it. And so that's why there's the most complexity in that description in that paper. So the first point is using open source tool chains. And we realize that it's not something that you can always get, right? You can't always do that, but if you don't try, it's totally not going to happen. And the reason for that is if I design something in, say, SolidWorks, right? If I design some mechanical parts in SolidWorks and I put those solid part files up on a repository, someone that isn't at a university or not at a major corporation probably won't have the means to do anything or modify those files. And so that's why when you're doing open source designs, you want to try and use open source tools that everyone can get easy access to. And so that's why I teach things like OpenSCAD and Arduino and things along those lines, because I know that you will always be able to get access to them because they're free and open source tool chains. It should be the same thing, though to a smaller extent, with the actual hardware, right? If you can use open source 3D printers and open source mills and things along those lines, it just kind of helps if you're staying in that open source ecosphere. But the tools aren't as important just because there are lots of other equivalent functionality tools out there. Like I can buy an open source 3D printer or a closed source, and they function about the same. But that's not quite the same with software. So that's why software is the really biggest catching point on point A. So point B is to minimize the number of parts and the complexity. And so that means a couple things, right? Minimizing the number of parts, right? You don't want to have a bunch of labor to make something if you can avoid it. And that's minimizing the total number of parts and unique parts, right? Because if I can just put like the same part and have it like bulk print, that's really nice. So minimize the number of parts and the number of unique parts. That also means that if I'm going into some sort of production of these open source tools, right, I can stock a small amount of unique parts because my tools use few unique parts. So it's just kind of an efficiency thing. And the other point is complexity. Obviously, if you can make things that are easy to 3D print, that's an important thing. But also, and this is something that I think gets overlooked, especially in software, is you want to try and do things as simply as possible, because especially when it comes to programming, if you are invoking some programming methods and libraries that are really complex to use, it becomes really prohibitive for someone to go in there and make modifications because they need to have a degree in computer science to be able to make those changes. And so my philosophy is I always try and use really simple libraries and only go into complex functionality if I absolutely have to. So yes, that's not just a 3D printing thing, that's also just a general software thing. Point C, it's a pretty standard thing that you would hear an engineer say, right? Minimize the material and the cost. One of the biggest advantages of open source hardware that we show time and time again in pretty much any paper I've wrote is that open source hardware can be way cheaper than closed source. But that doesn't happen unconsciously. I mean, by using 3D printing, you have that built-in advantage, and by using distributed manufacturing techniques. But you still have to make sure that you're not seeking out expensive things intentionally, right? You want to always try and reduce that cost. So point D is maximize the amount of things that can be distributed, manufactured distributively, whatever. Anyways, so what that means, what distributed manufacturing is the opposite of central manufacturing, right? Where you've got some sort of factory. The most common thing is circuit boards, right? If I want a circuit board made, commonly what I'll do is I'll get my design and I'll contact a board fab house that's in China, right? It's a centralized thing. They make it and send it out to me. So the opposite of that is distributed manufacturing, where you have the tools and they're all distributed throughout the whole world, right? So that's things like 3D printers and circuit mills, right? Those are, in my opinion, the two biggest tools to be able to make all sorts of things. Anyway, so you want to increase the amount of parts in your design that can be distributively manufactured, and it's pretty self-explanatory the reason for that. But the reason is that if you want people to replicate your design, you want there to be a low barrier for them to replicate it. And so if the prerequisite is that you have a 3D printer, well, lots of people have access to them these days. And so that is something that other people will have the tools to replicate your design. The flip side of that is if you say something along the lines of, is that a swarm of bugs? Or is that a cloud? I think that's a swarm of bugs.
I think you're right.
That's disgusting. Anyways, so the flip side of that is having parts that, those are totally bugs. Excuse me. Yeah, just watch the bug movie take care of the Oreo situation. That's a huge swarm of bugs. Oh man, that's disgusting.
We've done this before.
Yeah, we've ran into a bunch of them before at nighttime. Remember? Anyways, so if I have something that needs to be like CNC'd, not a lot of people have a CNC sitting around. The Oreos are all gone. Okay, so I'll hurry up because I think this video is starting to ravel at the edges here. The next point is parametric customization. This isn't always possible, but this is a really good thing to make your design the definitive design, right? If you can make things so they're parametric, meaning that they're easy for people to modify, like they don't even have to know anything about the modeling software. They can just change parameters and have your design meet their needs. That's just going to make it way more powerful and appealing to scientists, right? Because that's the thing. When you're designing open source hardware, sometimes you're designing things for fellow hackers and things along those lines, but the essence that we were thinking of with this paper was open source scientific hardware. And so commonly when you're making open source scientific hardware, it's for other scientists who might not necessarily be good with things like CAD. And so by having parametric designs, that makes it easy for non-mechanical engineers or non-electrical engineers to go through and modify things. All right, and point F is using readily available parts. So these are the parts that you can't manufacture, like your 3D printed parts. So that means when you use bolts, right, use commonly available bolts, use stepper motors that are commonly available, all those things that if you can search them and find them really easily on Amazon, that's the way to do it. And once again, that seems pretty intuitive, and it is, but the one little asterisk I want to put on there, or the thing I really want to point out, is when you're making these low-cost open source designs, it is somewhat tempting to say, oh, you know what? I've got this old TV in my garage, and I can break out this vacuum tube, and I can use that as an amplifier. Well, that's fine. You just cut your personal cost, but now when someone goes to replicate that design, they're going to say, I don't have access to that old TV, and I can't find that vacuum tube anymore. So that's why you always need to make sure that you're using up-to-date parts that are commonly available when you're making design that you really want other people to replicate. So yeah, those are the 6 points that you really need to consider for open source design.